Merci. Thank you very much for the invitation and the chance to give a talk in this nice conference, even though it's unfortunately virtual. Well, not for people in Salle W, but that's for most, the rest of us, it's a virtual conference. All right, so I'm going to stay firmly off topic from the main theme of the conference. There are going to be Hamiltonians, but I will not describe any of them explicitly, nor their dynamics in any detail. But what I want to do is a bit of propaganda for what is one possible way to update things about symplectic geometry, symplectic mapping class groups, and automorphisms and Fukaya categories from the class of symplectic manifolds to slight generalizations, which some people here might know under the name of sectors, but there will be extra assumptions in that case. Some people might know as Lefschetz fibrations, but mine will not be Lefschetz. Some might know under other names. And I've chosen the name Landau-Ginzburg model, which is from mirror symmetry, just to be on neutral ground for a symplectic audience, so that we don't have an idea of what exactly this is, because I want to keep the talk very imprecise. Not quite, but. And so I should say most of the talk is not about ideas of my own, but inspired by the thought processes of Seidel, then Abu Zaid, and then the younger generation, Ganatra, Zach Sylvan, Andrew Hanlon, Maxim Jeffs. And there would be a very similar but very different talk about more or less the same ideas that people like Nadler or Ben Gamage or Ganatra, and Shende could give. And yet there's yet a different talk with probably the same content, but very hard to understand for a symplectic audience, that people like Kontsevich, Soibelman, or Kapranov, or Dekkerhoff could be giving about this. And the other disclaimer is many of the statements I make below, to the extent that any of them are precise ever, are either not quite proved in the level of generality I will state, or they are actually not proved, or the proof is not written. So, all right, so what is a symplectic Landau-Ginzburg model? So it's basically a symplectic fibration over, say, the complex plane. So it's a map from a symplectic manifold Y to the complex planes, where Y is a symplectic manifold satisfying some convexity property at infinity, so that I can do holomorphic curve theory, and with the property that the fibers are symplectic submanifolds whenever they're smooth. So the main examples I have in mind are going to be, in fact, Kähler manifolds with holomorphic functions. And in general, you should imagine that whenever I do holomorphic curve theory below, if I place myself in the sector world, I will want to assume that my complex structures are conical at infinity and adapted and so on for Wrapped-Floer theory or contact homology. But in the other settings I will discuss and focus on more, I will want an almost complex structure that makes this map W holomorphic. So I want the fibers of W to be almost complex submanifolds. So the starting point of maybe the whole study of symplectic fibrations and their Fukaya categories is the observation that a symplectic fibration determines a horizontal distribution, which is just the symplectic orthogonal to the fibers. And concretely, this is also spanned by the Hamiltonian vector fields of the real and imaginary parts of W. So symplectic parallel transport induces symplectomorphisms between the smooth fibers, and this allows us to transport Lagrangian submanifolds. So the main kinds of Lagrangian submanifolds we'll be interested in are fibered Lagrangians that project over paths, arcs in the complex plane, or they may be fibered somewhere outside of a compact subset. I will mostly want to impose my Lagrangians to be fibered near infinity as a method of controlling holomorphic curves using the open mapping principle for the projection. So it's been studied by various people. I think Seidel is the most recognizable name on this. The notion of Lagrangian vanishing cycle in such a symplectic fibration studies basically what happens when you go to the singular fibers and then monodromy around them. So a vanishing cycle is a Lagrangian submanifold of a fiber, of a reference fiber, which under parallel transport along the symplectic orthogonal towards some critical value will collapse entirely into the critical locus. So I am saying this in a way that's a bit opaque because I do not want to make too many assumptions about my critical locus. And then the fiber Lagrangian that lives over this path is called a thimble, even though the name is kind of abusive outside of a Lefschetz case. If you look up what a thimble is in the dictionary, then you'll find out that this is not what you want to have in mind anymore outside of the Lefschetz case. So the simplest and best known example of this is Lefschetz fibrations. It's something, say, in the complex world, this is just a complex Morse function on a Kähler manifold. And otherwise, it's something modeled on this. So it's the case where the critical locus of W is isolated and non-degenerate. And so in that case, the singular fibers are modeled on something like sum of the I squared equals 0 in the complex in C to the n. So this is a singularity called an ordinary double point. And in that case, it's well known that the singular fiber is obtained from the smooth one by collapsing a vanishing cycle, which is a Lagrangian sphere. And we're going to see some other examples where I will not discuss necessarily the vanishing cycles explicitly. But I want to give one more example, which is kind of maybe one of the simplest and most disturbing ones, to explain that I want to also allow the possibility of accidents at infinity. I'm being told by some of my students that there are names associated to that, like the Malgrange condition and things like that. But the basic idea is sometimes the topology of a fiber changes not by passing through a critical point inside the manifold, but by having a modification of the topology at infinity. So the simplest example is if I look at C star squared, which I project to the complex line by the sum of the two coordinates. And the slightly surprising thing is if I set, if I look at the fibers, the non-zero fibers of this are pairs of pants. The zero fiber is a cylinder, and the way this cylinder comes about is that two punctures of my pair of pants come together and merge to a single point at the origin. So in this case, I would say that there's a vanishing cycle, which is an arc connecting the two punctures, and that the thimble associated to the path towards the origin is the trajectory of this family of arcs over a path in the base. So in fact, if I take a piece of the real axis, the thimble is just r plus squared inside C star squared. All right. And again, so I'm going to assume that there's not too many critical values because that makes things difficult. But I do not want to assume that the set of critical points is finite or even isolated or even compact, because some of the best examples are settings where this does not happen. All right. So what is a Fukaya category? Well, it's something whose objects are Lagrangian submanifolds and where morphisms study intersections. Lagrangian Fleur theory, possibly with some forms of perturbations. And now in a non-compact setting, I need to say what kind of Lagrangians I want and what kind of perturbations I want to apply to them for intersections. So what you should have in mind is if you have seen Paul Seidel or some of his many disciples, including myself, talk about Fukaya categories of Lefschetz fibrations, sometimes in the last 20 years, this is a generalization of that. But I don't want to assume that I have a Lefschetz fibration. So I want Lagrangian submanifolds that are admissible, is the usual name. And what is meant by admissible, there's about as many different definitions as there are papers on the subject. So I'll try to interpolate some classes of possible definitions and convince you that you should not worry too much about which one is being used unless you're trying to prove a theorem that involves comparing two of those. Because basically they all have the same properties in practice, but it's sometimes just harder or possibly impossible to prove the property you want. That doesn't make it false. They should be the same category. It's just it's too much work to prove that they're the same. Anyway, so the objects we want to look at are Lagrangian submanifolds that do not go towards the, by convention, we take the real negative infinity direction of this vibration. So you want properly embedded or possibly immersed, if you like immersed Lagrangians, which avoid what's called a stop placed towards the real negative direction at infinity. One way to enforce that is to ask that actually all your Lagrangians go towards plus infinity. That's one good way of being away from minus infinity, but you can relax that. Some versions of the theory also just require you to be disjoint from some other subset of a boundary at infinity on which this thing retracts. So, this is a very flexible notion. If you work in the world of sectors, almost any kind of operation that doesn't change the nature of life is known to be allowed. So in any case, you will want, of course, to put extra conditions so that you can control holomorphic curves using some kind of maximum principle at infinity, including along the Lagrangian boundary. You want your Lagrangians to be unobstructed. That means they shouldn't bound any holomorphic disks, or if they do, you will want to deploy your favorite machinery like bounding cochains to cancel them. And you might want to decorate them with anything you want to do your favorite version of Floer theory, like a spin structure, a local system, grading data, and so on. The morphism spaces involve Lagrangian Floer complexes, as usual, but with a perturbation. And so what we want to do is push Lagrangians by a positive Hamiltonian isotopy that doesn't cross the stop. Okay, so positive here means basically that we want to rotate the base direction of our vibration counterclockwise at infinity, but never crossing the stop. So you might try to imagine some kind of flow in the base complex plane that goes around, but then never comes back to cross minus infinity. Meanwhile, in the fibers, what you want to do looks a lot like wrapped Floer theory. You might want to take a Hamiltonian perturbation, therefore, that grows quickly enough at infinity in almost every direction, except towards the real negative direction of the stop. So there are various techniques for building such perturbations. And that's basically the root of why there are so many versions of the category. Okay, so here's three main flavors, just so that you can have a picture in mind, and you can choose really whichever one. This is a choose your own adventure kind of talk. You can choose your favorite version, but you'll see that the third version that I will try to explain at the end is the one that has most of the features I want readily visible. All right, so first way of doing this, which goes back to basically Seidel's thesis, I would say, is to consider Lagrangian submanifolds which, outside of a compact subset, are fibered and fiber-wise compact. Sorry, I've switched from compact to proper because I've talked to too many algebraic geometers in the recent years, and but proper means compact, okay, in this talk. So outside of a compact subset of Y, so basically inside each fiber, you have a Lagrangian submanifold, and these Lagrangian submanifolds are compact fiber-wise, and they live over unions of paths in the base. So, for example, the Lefschetz thimbles of a Lefschetz vibration studied extensively by Seidel are a good example of that. So what you do in terms of perturbation then is you just push things a bit in the base. So you have something that fibers over a given path, and you push the path in the base, and you can redo your parallel transport, or you can define a Hamiltonian which does this kind of perturbation. And then the Lagrangians are in the correct position as soon as all the ends of one are counterclockwise from all the ends of the other, still without crossing -infinity. And so this is all you need if you don't need to look at Lagrangians that are fiber-wise non-compact. Then it's enough to look at fiber-wise compact objects, because what these categories are supposed to do is probe the relative topology of a total space relative to the part, say, near -infinity, relative to the stop. And so if a fibration is trivial at fiber-wise infinity, you can retract everything so that only a bounded subset of the fibers matters. So there's a statement which, in the case of Lefschetz fibrations, is in Seidel's book, that will say that fiber-wise compact objects generate, and so you don't need to worry about adding on some fiber-wise perturbations at infinity. All right. The next thing I might want to do, instead, jumping ahead in technology. So far, this is only known how to do in the exact setting for Liouville manifolds, is view things instead in terms of wrapped Floer theory, but modifying the wrapping by either slowing down the Hamiltonian in near the stop, or by filtering wrapped Floer theory by intersection numbers with the stop. So this is Sylvan's partially wrapped Fukaya category, or the language of Liouville sectors of Ganatra, Pardon, and Shende. So in this setup, you would assume that your Lagrangians are conical at infinity for the Liouville structure, and then you would modify basically wrapped Floer theory to just take the stop into account. So this is extremely powerful because we know from Ganatra, Pardon, and Shende that there are a lot of structural properties like covariant functoriality for inclusions of sectors, gluing results, and so on. So computationally, if you have a description of your manifolds in terms of skeleta, and in this case, relative skeleta relative to the stop, then you can land in the micro-Sheafy world and forget symplectic topology. The main examples I like are not of this kind. So even for the ones you'll see today are all exact. Maybe one note here is for the things I will explain later. I don't want to consider an arbitrary Liouville sector. The stops of Landau-Ginzburg models have an extra property which is sometimes called being swappable. So a swappable stop in a sector means sector, is a Liouville manifold but with a boundary, which is where the stop is. And swappable means that a negative ray push-off of a stop and a positive ray push-off of a stop can be isotoped to each other by a Hamiltonian isotopy that fixes the stop. And how we do that in a fibration, of course, is by pushing things around in the base of a fibration. A general sector does not need to have a fibration describing its stop, and then it's not automatic that you can push things all around from the stop back to itself. So the difficulty with what I'm about to explain now in the sector world is that the wrapping is usually, everything is set up so that the conical structure wins, and the fibration gets forgotten in the process. And I'm going to want to focus on the geometry of the fibration. So that's why sectors are not always straightforward to use in the kinds of manipulations I want to do in the rest of the talk. So finally, maybe the least well-developed, but I think this is like what I would like to advertise notion here, is something called monomial admissibility. It's called monomial because this got done first in the case where y is a toric variety, and we use monomials. But you could imagine doing this with other sets of functions instead. So the only really well-written, readable reference that actually exists is the thesis of Andrew Hanlon for this. the idea is you equip your space Y with a finite collection of distinguished functions. In the toric case, a certain collection of toric monomials, and you require two things. One is that you have enough of these so that altogether they define a proper map to some affine space C to the n. And the second requirement that will be clear in a moment is that the stop or the fiber of a vibration can be expressed in terms of those. So concretely, that means W needs to be a linear combination of these functions. Maybe I should write that somewhere, because so W is in the linear span of these things as well. Okay, so, and then admissibility is the following thing. So first, we'll describe a way of subdividing the complement of a compact subset of Y into an open cover indexed by the same kinds of things as these monomials. And there's a condition, which I don't want to state exactly, which says basically U sub nu has to contain the set of points where Z to the nu is the largest of the monomials under consideration. Okay, so you should imagine U sub nu is where Z sub nu is the largest of the Z to the nu's. That's a slight lie. You need to generalize this a little bit more. And then admissibility will say the argument of Z to the nu is locally constant at infinity on the part of a Lagrangian that lives in U nu. So what does that say? What that says is I want my Lagrangian to be fibered not just for W, or maybe not necessarily for W at all, but rather for each of a collection of monomials that may or may not appear in this function W, but enough such functions that I have a collection of maximum principles, open mapping principles for each of these functions in different regions near infinity. And then I can have a good control over holomorphic curves by applying the maximum principles to all of these projections. And then there's a process to construct Hamiltonian perturbations where you just increase the value of the arguments of these functions near infinity. So if you are for the terms which appear in W, say that W is one of these functions, for example, then increasing the argument will be done always without crossing pi. We don't want to go to the negative real direction. That's forbidden. For the others, we can increase arbitrarily much, and that's how we can implement wrapping. So this is kind of wrapping and fiberedness combined by hand in a very limited setting. But the advantage when this works is that this version of the Fukaya category has more properties than the others. Well, probably it has the same properties as the others, but they're easier to prove. Okay. All right. So, sorry, I'm still going to introduce more complication into this story. So what I would like to say next is in real life, and this is kind of what the point of monomial admissibility is, you might not want to think of a single vibration as being a unique thing. You might want to think of a vibration as being a sum. A function might be a sum of different simpler functions. And you might want to break things into these different simpler functions. That's kind of what monomial admissibility enforces by saying, okay, you have to use these monomials Z to the W and treat each of them separately. So in particular, I might want to think that there's a main term in W, W0, and an auxiliary term, WF. And WF, what it might do is define a stop on the fiber of W0. So what that means is I want to decompose the stop of YW, the region where W becomes negative large, into the part where this is because W0 becomes negative large, and the part where this is because the auxiliary term becomes negative large. And now I might want to explore the geometry of Y not relative to the whole stop or the whole fiber, but only relative to the fiber of W0. Why might I want to do that? One reason is mirror symmetry. The examples that will come up in a moment are from mirror symmetry and tell you why this is good. But maybe a more intrinsic way to think about this is, well, we've been saying we like to think about symplectic fibrations, and we think symplectic fibrations should be first-class citizens in symplectic topology. Well, if that's the case, we should consider fibrations whose fibers are themselves Landau-Ginzburg model. And this is what this does. W0 is the fibration, and the fibers of W0 are themselves Landau-Ginzburg models or sectors. And of course, there's a compatibility requirement to be able to do that. You need parallel transport in the fibers of W0 to preserve admissibility in the fiber-wise categories. So the disclaimer is in known examples that are non-trivial, this requires actually taking a bit of care in choosing the Kähler forms and doing the whole setup. But so the expectation is that you get the same Fukaya category whether you work directly with W as a single fibration, or if you try to break it into a sum of two things and view things as Lagrangians that are fibered for W0, the main term, and fiber-wise admissible for WF, and do things in stages. So maybe to backtrack a bit, one of the greatest, I think, insights that came out of Seidel's work 20 years ago is that we can understand Fukaya categories of symplectic manifolds by a dimension induction process, where you have a total space, you have the fiber, and you have the category of the fibration sitting neatly in between, giving you an interplay between the two. And the statement here is we can do the same for sectors with swappable stops or for Landau-Ginzburg models. And so monomial admissibility basically builds this into the setup, that you will separately be able to break off terms from your function W and treat some of them as more important than others. All right. Okay, so here's a possible way of saying slightly more precisely what is the fiber-wise wrapped Fukaya category using monomial admissibility. So let's say we have a toric variety, and we have a function which is a sum of toric monomials, and I will break off one of them that I will call W0. So the objects of my category will be properly embedded Lagrangians, which are unobstructed, carry extra data, and so on. And the admissibility condition will basically say, for the main projection, I'm separating the main projection from the others just to make it apparent, but the condition is in fact kind of symmetric in all the terms. Whenever the main projection is large, the argument of W0 is locally constant. So what that means is the projection of my Lagrangian under the main projection W0 might have a blob in the interior, but at infinity, it's a union of radial arcs, and none of these arcs go to the negative real direction. And then inside the fibers, I will have, so in fact, because W0 is a monomial, the fibers of W0 are toric varieties, some of them singular. And so we impose again admissibility with respect to toric monomials on these fibers. And I want these monomials to include all the terms that appear in WF, the auxiliary potential. And so that means I will require the arguments of these to be locally constant at infinity in each fiber. Okay, but what I've done here is I've kind of separated W0 artificially because that's the picture we will have in mind, but you can formulate the definition in a more symmetric way. All right, so these admissibility conditions both give us control on holomorphic disks and also tell us what kind of perturbation to take at infinity. So admissibility allows us to, is preserved, under the flow of certain Hamiltonian perturbations, which increase the arguments of all these monomials we discuss at infinity in the appropriate regions. So we have these various monomial quantities whose argument has been prescribed, and the claim is we can modify the values by some Hamiltonian perturbations. How much do we modify them? By a little bit, just to push them past each other. If I'm looking at the terms that appear in W, the directions that are stopped, that should never cross the negative line. And otherwise, we want to wrap, which means we want to let the argument of those variables go all the way to infinity. So basically, Andrew Hanlon's thesis explains it's actually very simple. You just use things lifted from the moment polytope satisfying suitable slope conditions in different regions. You can build a set of Hamiltonians with these properties. And then you define morphisms to be limits of Floer complexes under such perturbations. Okay. And so the guess is that, I hope we can make such a definition also outside of a toric setting, but I don't know yet how one would do that. And of course, the other hope is that this agrees with other versions of Fukaya categories. This is known basically for C star to the n and Laurent polynomials by Hanlon's thesis, but that's kind of the only case. All right, so here's an example at last. I've been talking in the abstract. So my favorite example of this is C cubed with the product of the coordinates. And for now, there's only a W0. There's no extra terms. So this is, in mirror symmetry, this is a mirror to a pair of bands viewed as maybe a curve in C star squared defined by the equation 1 plus x1 plus x2 equals 0. So my favorite Lagrangian in this is obtained by parallel transporting between the fibers something which is just r plus squared in a reference fiber. So what are the fibers of this map? Right. So if I set W0 equal, Z1, Z2, Z3 equals constant, that's C star squared, unless I take the 0 fiber, which is singular, and a union of three copies, the three coordinate planes. Now the fiber at -1 is a copy of C star squared, and in there, there's my favorite Lagrangian, which generates the wrapped Fukaya category of C star squared, is r plus squared. Okay? And the wrapped Floer homology of r plus squared in C star squared is in fact a ring of Laurent polynomials in two variables. So now what I will do is I will upgrade L0, this little L0, to an admissible Lagrangian by parallel transport over a U-shaped arc. And this will be admissible both in the vertical infinity, where the arguments of the largest of Z1, Z2, and Z3 will be fixed, and in the base infinity, where W0 moves along two radial lines, fixed argument. So this is what monomial admissibility looks like, these conditions at infinity. So the condition is that the argument of Zi is 0 whenever Zi is one of the largest. And then we wrap. So we push things around by moving our U-shaped a little bit counterclockwise, just enough that the legs cross each other. And in the fiber, we let go, we wrap as much as we want to do wrap Floer theory in C star squared. So what is the self-Floer homology of this? With these perturbations? Well, I should probably stop with all these decorations so that we can see again what's happening. So there are two places where L0 and its perturbation intersect over these 2 points in the base. In this place, in the main fiber at -1, I see the wrapped Floer homology of r plus squared with itself. That's a copy of Laurent polynomials in two variables, basically because, I take r plus squared where the arguments of the complex variables are 0, and when I wrap, I push the argument around the argument torus as much as I want. And it's the product of the wrapped Floer, the tensor product of the wrapped Floer homology of an arc in a cylinder with itself. Okay, so I get Laurent polynomials in two variables. In this other fiber here, I get, in fact, a very similar picture. Everything is slightly deformed by the parallel transport and the monodromy around the singular fiber. But once you wrap enough, it's still the Wrapped-Fleur theory of two Lagrangian sections in C star squared, or cotangent fibers in T star T2, if you like that better. Okay, what else? There's a Fleur differential, because there are holomorphic disks over this region here. So you need to count holomorphic sections over this region, and there's a calculation to be done, and the answer is that that differential is multiplication by 1 plus x1 plus x2 on Laurent polynomials in x1 and x2. And so the Fleur cohomology after perturbation is the quotient of Laurent polynomials by the ideal generated by 1 plus x1 plus x2, which is also the ring of functions on this mirror pair of bands. And this is a ring isomorphism. The multiplicative structure matches. So this basically is, I've explained here the heart of the proof, that this satisfies, this and the pair of bands satisfy homological mirror symmetry. The Fukaya category of this fibration is equivalent to coherent sheaves on a pair of bands. You can do now a modification of this example where I will add a fiber-wise potential. Okay, let me add some constant times Z1 plus Z2 plus Z3. One option is you can say, forget all this nonsense, I will recalculate things, and I will find that this is actually a Lefschetz fibration with two singular fibers, and I can calculate the category using Seidel's old-fashioned techniques. I'm not sure if calling it old-fashioned is the right thing to say, but in this field it kind of is. Okay, but instead what I would like you to think about is that this, if I think of this as an extra thing that I put on the fibers of W0, the fibers which were C star squares now become C star squares equipped with the restriction of Z1 plus Z2 plus Z3, which looks like basically Z1 plus Z2 plus constant over Z1, Z2. The constant depends on which fiber you look at. So by a happy coincidence, actually it's not a coincidence, this Landau-Ginzburg model that we now put in the fibers is known to be the mirror of CP2, whereas C star squared without a potential was mirror to C star squared. And so if you redo the calculation, but you slow down, so the main difference is now you stop the wrapping fiber-wise. You only push a little bit in the fibers instead of a lot. Then you will find that you end up with something that looks like the derived category, no longer of a pair of bands, but its compactification to a line in P2. So the slogan mirror symmetry-wise here is that adding terms to a potential is mirror to a partial compactification, or in this case, a complete compactification. So this kind of method actually gives a lot of mileage. You can prove homological mirror symmetry for complete intersections in toric varieties, essentially for free, once you really understand the definitions and this example. This is something that Mohammed Abu Zaid and I have been talking about a lot and not writing up enough of. So you don't necessarily need to believe it, but this is computationally very useful. You can build basically the mirror of a complete intersection in a toric variety in pretty much all generality is going to be something of this kind. A toric variety with a main monomial, or several if you have a complete intersection, one for a hypersurface, and auxiliary monomials that pin down things and compactify from C star to the N to a toric variety. Anyway, but that's what I would spend the rest of the talk on if I were talking to mirror symmetry people. Instead, I want to go back to some symplectic geometry. So what's interesting to a symplectic geometer, I hope, is that the Fukaya categories of these total spaces and of the fibers are related by a large number of functors in all sorts of directions. Maybe when you say the F word, then maybe some people tune out, but this is trying to explain basically some of the structure here. So there's something called a spherical functor, which if you know what that is, you will laugh at me for trying to explain it. But I didn't know what that was. I still don't really know. So I'm going to just tell you what that looks like. So the claim is, we have two categories we want to look at. One is that of a fiber. So the fiber, by that I mean, again, the fiber of W0 together with the auxiliary potential WF, so function WF. And then there's the big space. So the claim is there's two functors usually called cup and cap between these two in opposite directions. So cup from the fiber to the total space is in fact what I just did to this poor little L0 in the previous example. You take a Lagrangian in the fiber, admissible for the auxiliary thing WF, and you transport it along a U shape in the base of W0. So you end up with a Lagrangian that has two ends. One of those looks like L, and the other one looks like the image of L under the monodromy around all the singularities. Okay, so this is cup L. In the opposite direction, given a Lagrangian in the total space, I can restrict it to a neighborhood of plus infinity. In the monomial admissible case, I just do that because it's fibered over a bunch of things. In the sector world, what I do is I restrict to a subdomain that lives near infinity, and I need to I land in the stabilization of the fiber as a sector, but that's not a big difference. So the ends at infinity, now there might be several, and so what I get is not a single object of the category of a fiber, but rather a twisted complex, in which, in fact, there's a connecting differential, which comes from a count of holomorphic sections of the base. But maybe I shouldn't get into these kinds of technical things. So you can ask, what happens if I do cap then cup, or cup then cap? Okay. So if I start from a Lagrangian in the fiber, I transport it over a U shape, and I restrict, then I see two ends. The Lagrangian I started with, and its image under the monodromy. And I get a mapping, the mapping cone of some morphism between those that counts sections. So what this says is, in fact, that these functors fit into exact triangles with some monodromies. So there's two monodromies at play. One is the monodromy of W0 around the origin acting on the fiber. I take a Lagrangian in the fiber, and I move it around. This is exactly the mu that showed up here, except it's mu inverse because of directions. There's two conventions. I'm giving you one of the two conventions here. Okay. And then there's another kind of monodromy acting on the total space, which I'll explain further down, which corresponds to wrapping once through the stop. And the slogan of spherical functors is, now this diagram in its entirety looks symmetrical between left and right. And that's exactly the point I'm trying to get to today. So there's exact triangles of functors. That's a fancy word for explaining what I just said, that if I take a Lagrangian in the fiber, I spread it over a U shape, then I re-intersect with the fiber, then I get something which is built out of what I started with, and its image under the monodromy. And in fact, what I get is a twisted complex with a differential that counts some sections. So S, in fancy language, is a natural transformation from the inverse monodromy to identity. You could also do from identity to monodromy. That's the same thing. That was, I think, first discussed by Seidel. And what it does is, given any Lagrangian in the fiber, you move it over this fish shape instead, and you count holomorphic sections with boundary conditions over the enclosed region with an output condition here that gives you an element of a Floer complex of mu inverse L with L. In our setting, you add wrapping to all that, but that's not really a change of anything. And in the opposite direction, there is an exact triangle of functors in the opposite direction between, involving now cup cap, which starts with something in the total space. You restrict to its end at infinity, you push that end around, and then what that does is it gives you something So if I start with an L, cup L is its end at infinity. Cap cup L is a U-shaped Lagrangian with the same end as L. So if I do a connect sum operation between the two near this infinity here, I end up with something which is the image of L under twisting it once around the plane. So this is a diffeomorphism, actually a symplectomorphism of a total space, which is identity in a compact set. Identity at infinity, but inserts a 2-pi rotation in the base of a fibration in between. This is also something that Seidel has considered abundantly. And so this fits into another exact triangle of functors. The connecting map now is a continuation element for basically the isotopy that goes from identity to this negative twist by 2-pi. All right, so what do we do with all these functors? First thing you can do is go crazy or get excited, and that's kind of a natural place to start. But then at some point you want to say something about them. So first thing I want to say about them, basically there's two things I want to say. I guess I will have time for one. So this is again the same picture. One thing to say is that in mirror symmetry, these things are very useful. So there's one setting, for example, when you do mirror symmetry for a Fano manifold, that means something simpler than Calabi-Yau, relative to a divisor which is smaller than the anti-canonical. So that means, for example, you could take CPn relative to a hypersurface of degree at most n. So then the claim is you have mirror partners, which are such Landau-Ginzburg models, in which the mirror to the total space is, the total space is mirror to your variety X, and the fiber of the main potential with the auxiliary potential is mirror to this hypersurface, D0, which is part of an anti-canonical divisor. In this case, these cup and cap functors and all the adjunctions between them correspond to inclusion and restriction between vector bundles or coherent sheaves or whatever on X and on this hypersurface. For example, if I take the mirror to CP2 and I just look at the whole thing at once, no WF, then the fiber is a 3 times punctured torus, and these functors correspond to restriction and inclusion between CP2 and, in fact, the total toric divisor, the union of the coordinate planes in CP2. On the other hand, there's constructions of mirror symmetry for hypersurfaces, like the pair of pants I was telling you about. And what happens there is backwards. The total space is mirror to the hypersurface. The fiber is mirror to the ambient space in which this hypersurface lives. And then the interpretation is reversed. For example, in my C cubed XYZ, I said this total space, its Fukaya category, corresponds to the pair of pants, and the fiber-wise category was C star squared, the space inside which the pair of pants lives. And this cup construction that I used to build my favorite Lagrangian on this side is exactly corresponding to the restriction now from, the two sides of the picture are backwards, but anyway, yeah. I've drawn my example. I mean, here I've written the fiber on the left, total space on the right, but in the examples, it should have been switched. I mean, the fiber, this is the fiber, this is the fiber. All right. So the question is, why this reversal? And so this is kind of maybe the punchline I want to get to. No, I don't care about this. The point is there is a stabilization process that you think you can do, probably, which is given such a space, Y with fiber F, carrying an auxiliary WF, you can take the product of Y with the complex plane and put some, build some bigger function, which kind of looks slightly crazy. So what does this do? The first thing is, if I look at this main function here, this is Morse bot, and it's Morse bot with critical locus being at z equals 0, w0 equals t. So its critical locus is, in fact, a copy of the fiber of my smaller space. And what that will imply is that the Fukaya category of this total space should be equivalent to the category of the fiber by a stabilization process where I take Lagrangians in F and I upgrade them by parallel transport under this to Lagrangians in Y tilde. And meanwhile, if I now break this differently into splitting Z from the rest, on the levels of Z, well, because Z is the complex coordinate, the levels are Y equipped with W0 plus WF. So I've swapped the total space and the fiber. And so the claim is up to another, various technical issues which make this not quite accessible, and up to a basic fact of algebra, which is that we're swapping the direction of adjunction. So you need to kind of do a small algebraic manipulation. This exchanges fiber and total space. So what is this good for? Now, I promise I get to the last point. What I want to get to is that these sorts of ideas let you define the Fukaya category of a singular manifold. So the process is to now ask, what do you get in this diagram of categories and functors if you take a localization? So I'm going to focus just on this one here. If I localize the category of a fiber along this natural transformation that counts sections. So what I mean is I make the so because of the exact triangle, let's just say the easiest thing, this is the same as quotienting by the image of a cap functor. So quotient the Fukaya category of a fiber by the vanishing cycles. So you can ask, why would I want to do a quotient of a Fukaya category by something? Well, when you look at a fibration with just one critical fiber, you can think of this as a candidate definition for the Fukaya category of a singular fiber. So if you want to ask, algebraic geometers keep asking symplectic geometers, how come you guys can't work on singular spaces? Well, it's a fact of life, we can't. We are differential geometers at heart, and we just don't know how to do that. But, the next best answer you can tell them is, okay, if my singular space has a smoothing, because it comes as a fiber of a function, complex valued function, then, okay, here's a candidate definition. Take the nearby smoothing and quotient the Fukaya category by the image of this cap functor. And so this works very well for things like singular mirrors to pairs of pans and so on. The other way you could do this, if you don't like this sort of yoga, is do the stabilization I suggested in the previous slide, which in this context just means you take the product of the ambient space Y with complex line, and then you take the potential on that, which is the complex coordinate times this function W0 that was defining your F. And the claim is that, so that's a theorem of my student Maxime Jeffs, under suitable assumptions in the affine case, basically, the wrapped Fukaya category of a singular hypersurface, as defined just above by quotienting, is equivalent to the Fukaya category of a stabilization. And so this I would like to suggest is one way to, rather these are two ways which are fortunately equivalent, either stabilization or localization, of extending the notion of Fukaya category to a singular symplectic submanifold, manifold which comes naturally as a singular hypersurface in some ambient space. And of course, it probably depends on the choice of smoothing. All right, so I should probably stop here. Thank you for your attention. Sorry for the slightly rushed amount of things at the end.
Thank you. So, is there any questions?
I can ask a question. So, Denis, towards the end, your punchline was you have a candidate for Fukaya category of singular symplectic manifold.
Mm-hmm.
But if you go down a little bit, like what's the candidate for Floer homology of a singular Lagrangian? This should contain that.
It might or it might not, because that depends on whether your singular Lagrangian comes out of comes from a limit of a family of smooth Lagrangians in the ambient space. So what this is pointing to, I think, is wait, I almost kicked you out. Good thing I was trying to go forward in my presentation, not backwards. I almost kicked myself out of a meeting. That's all right.
You're always
So
welcome back.
sorry.
You're always
No,
welcome.
the problem is if I press back in the browser instead of in my presentation, then Firefox asks me to reconfirm 8 times with the passcode and everything, and whether I want to share my camera and do I really want to share it. So if I press back in my web browser, it's game over for the next 10 minutes. Okay, so what am I trying to say? So let's say, here's a good example. Let's take a torus, and let's take a singular version of a torus, which is, squish this curve on my torus. So now I might want to know, what does this kind of Lagrangian have as a Floer homology there? And so the answer right now is it's going to be the limit, basically, of taking this thing and taking its image under successive Dane twists, in fact, about this. So I should draw that like some sort of infinite Dane twist process along the curve that I squished, is what this interpretation is giving rise to. Now, if you were to ask me instead, okay, I want to do Floer homology for a singular, I can't do that in this dimension, but some kind of singular Lagrangian on a smooth symplectic manifold. The answer to that is I don't know. This does not come up in my world. Now, I do know from other work, right? There's like ideas of, for example, Lekili and Ekholm, I think, and other people. I forgot now who are all the, there's a bunch of papers about that, where I think the main answer I would give is, what they say is cut out something here, treat that as something with a concave contact end, and now you get invariants in the complement which land in the contact homology of this Legendrian link of the singularity. And of course, for that, then you need to have a moduli space. You need to choose a linearization of the contact homology to be able to define things outside. And so then you can ask, what is the moduli space of objects actually that live on this? What are the possible choices of linearized contact, spaces of augmentations for this piece that you're dealing with separately? But that's kind of a different flavor of things than what I'm doing.
Yeah, so I think the name you were looking for is that of Johan Asplund.
Oh, yes. But I thought there was also a paper by Ekholm Lekili, right, on this, maybe.
It's all intermingled, but yes. Okay, thanks a lot.
Sure. Yes, Elsa.
I have a kind of philosophical question. Going back to the stuff you were telling us about your work, possibly with Mohammed, extending Andrew's setup, how far do you think that can go?
That's a good question.
Set up all the way to have the same kind of generality as GPS, or is there a kind of heuristic reason why it should only be a smaller class of Landau-Ginzburg potentials?
So I don't really know. I think no. I think there's probably going to be more restrictions, but more importantly, there's more choices. So the first thing to do is to actually try to understand more about the independence of choices already in this setting, right? Because, for example, here I've actually, imposed. I've chosen a whole set of toric monomials that I want to impose admissibility for. For some of them, it's part of because they're inside my function W, but for some of them, it's a technical tool to control holomorphic curves. And the ones for which it's purely a technical condition, I will wrap fully by increasing, I will wrap in those directions completely. The question you can ask is, does it depend which ones I chose? And so Hanlon's thesis contains a comparison result with Abu Zaid's version of a Fukaya category of toric varieties, which says in some cases it doesn't. But to formulate those conditions properly outside of a toric setting, I don't know. So by the way, Hanlon does only y equals c star to the n, but I claim that y a toric variety should be a mild generalization. That in itself has not been written or checked.
Yeah,
but that's what I'm confident about. Outside of that, I don't really know.
Okay, that was what I was wondering. Thank you.
Any other questions? There is no question on the chat, so maybe we can thank Denis again